In this video, we're going to be looking at polar coordinates. Let's begin by actually looking at another coordinate system, the Cartesian coordinate system. Now, in that system, we take two axes, an x-axis, which is horizontal, and a y-axis, which is vertical, and a fixed point O, called the origin, which is where these 2 points cross, these two lines cross. Now, we fix a point P in the plane by saying how far it's displaced along the x-axis to give us the x coordinate, and how far it's displaced along the y-axis to give us the y coordinate. And so we have a point P, which is uniquely described by its coordinates x, y. And notice I said how far it's displaced, because it is displacement that we're talking about and not distance. That's what these arrowheads that we put on the axes are all about. They're about showing us in which direction we must move, so that if we're moving down this direction, it's a negative distance, a negative displacement that we're making. Now, there is more than one way of describing where a point is in the plane. And we're going to be having a look at a system called polar coordinates. So in this system of polar coordinates, we take a pole, O, and we take a fixed line. Now, how can we describe a point in the plane using this fixed point, O, the pole, and this baseline here? Well, one of the ways is to think of it as, what if we turn around? Centering on O for the moment, we rotate around. We can pass through a fixed angle. Let's call that theta. And then along this radius, we can go a set distance. And we'll end up at a point P. And so the coordinates of that point would be r theta. And this is our system of polar coordinates. Now, just as we've got certain conventions with Cartesian coordinates, we have certain conventions with polar coordinates. And these are quite strong conventions. So, let's have a look at what these are. First of all, theta is measured in radians. So that's our first convention. Theta is measured in radians. Second convention. Well, our second convention is this, that if this is our initial line and this is our pole, then we measure theta positive when we go round in that direction, anti-clockwise, and we measure theta negative when we go around in that direction, which is clockwise. So in just the same way as we had an arrowhead on our axes x and y, in a sense we've got arrowheads here distinguishing a positive direction for theta and a negative direction for measuring theta. We have a third convention to do with theta, and that is that we never go further round this way. Remember, there's our pole, O, our fixed point. We never go further round this way than there. So theta is always less than or equal to pi. And we never go round further that way than there again. So theta is always strictly greater than minus pi. Minus pi round to there, plus pi round to there. And notice that we include this bit of the line, if you like, this extended bit of the line, by going round to there, having the less than or equal to, and having strictly greater than, theta strictly greater than, minus pi there. A fourth convention. A fourth convention is that r is always positive. One of the things that is quite important is that we be able to move from one system of coordinates to another. So the question is, if we have a point in our xy plane whose coordinates are x and y, how can we change from Cartesians into polars, and how can we change back again? Well, one obvious thing to do is to associate the pole with the origin, and then to associate the initial line with the x-axis. And then if we draw the radius out to P, and that's r, and that is the angle theta. So we can see that in Cartesians we're describing it as xy, and in polars we're describing it as r theta. So what's the relationship between them? Well, let's drop that perpendicular down, and we can see that this is a height y because of the y coordinate of the point, and this is at a distance x because of the x coordinate of the point. And looking at that, we can see that y is equal to r sine theta, and x is equal to r cos theta. So given r and theta, we can calculate x and y. What about moving the other way? Well, from Pythagoras, we can see that x squared plus y squared is equal to r squared. So given our x and our y, we can calculate r, and we can also see that if we take the opposite over the adjacent, we have y over x is equal to tan theta. So given a y and an x, we can find out what theta is. Now, always when doing these, it's best to draw sketches. If we're converting from one sort of point in Cartesians to its equivalent in polars, or if we're moving back from polars to Cartesians, draw a picture. See where that point actually is. Now, want to have a look at some examples. First of all, we're going to have a look at how to plot points. Then we're going to have a look at how to convert from one system into the other, and vice versa. So let's begin with plotting. Plot, and what I'm going to do is I'm going to plot the following points, and they're all in polar coordinates. I'm going to put them all on the same picture so we can get a feel for whereabouts things are in the polar plane, or the plane for the polar coordinates. So we put our pole O, and we have our initial line. The first one that we've got to plot is 2 pi. So we know that pi is the angle all the way around here. So there's pi to there, and we want to go out 2 units. So it's there. And this is the point 2 pi. Next, the point 1, 0. Well, theta is 0, so we're on the initial line, and 1 will be about there. So there is the point 1, 0. 2 minus pi by 3. Well, minus pi by 3 means come round this way. And so minus pi by 3 is about there, and we're coming around there, minus pi by 3, and we want to come out a distance 2, so that's roughly 2 out there, so this would be the point 2 minus pi by 3. And finally we've got the point 1, 2/3 of pi, so we take the 2/3, that's going all the way around to there, and we draw out through there, and we want a distance of 1 along there, which roughly, according to the scale we're using, is about there. And so that's the point 1, 2/3 of pi. Notice that we've taken theta first to establish in which direction we're actually facing. Okay, let's now have a look. Having got used to plotting points, let's now have a look in polar coordinates at these points, 2 minus pi by 2, 1 3/4 of pi, and 2 minus pi by 3. Now these are all in polars, and what I want to do is convert them into Cartesian coordinates. So first, a picture. Whereabouts are they? And I'll do them one at a time. So let's take this one, 2 minus pi by 2. Initial point, pole, O, and initial line. Minus pi by 2, well, that's coming down here to there. So that's minus pi by 2, and we've come a distance 2 to there. Well, we don't need to do much calculation, I don't think, to find this. If, again, we take our origin for our Cartesians as being the pole, and we align the x-axis with our initial line, and there's our x, there's our y, and we can see straight away that the point in polars that's 2 minus pi by 2, in fact, goes to the point in Cartesians that's 0 minus 2, because it's this point here on the y-axis, and it's 2 units below the x-axis. So it's 0 minus 2. Notice how plotting the point actually saved us having to do any of the calculations. So let's take the next point now, which was 1 3/4 of pi. 1 3/4 of pi. So again, let's plot where it is. Take our initial point O, our pole, and our initial line. 3/4 of pi going round, it's positive, so it's round to there, be somewhere out along that direction. There's our angle of 3/4 of pi. And we're somewhere out here at a distance 1 unit. So again, let's take our x and y axes, our x-axis to be along the initial line, and our y-axis to be vertical and through the pole O, so that the pole O becomes our origin O. And it's this point that we're after. Now, how are we going to work this out? Let's remember the formulae that we had. It was x equals r cos theta. So let's have a look at that. R is 1, and we've got cos of 3/4 of pi. And the cosine of 3/4 of pi is minus 1 over root 2. So that's minus 1 over root 2. Y is r sine theta, And so this is 1 times the sine of 3/4 of pi, and the sine of 3/4 of pi is just 1 over root 2. And so we have 1 over root 2 for our y coordinate. And notice that these answers agree with where the point is in this particular quadrant, negative x and positive y. Negative x and positive y. So even if I've got the calculations wrong, in the sense that even if I've done the arithmetic wrong, I know I've got the point in the right quadrant. Let's have a look at the last one of these. 2 minus pi by 3. So again, our pole, our initial line. Minus pi by 3 is around here. So we've come around there. Minus pi by 3. And we're out a distance 2 along there. Take our x-axis to coincide with the initial line. And our origin to coincide with the pole. Let's write down our equations that tell us x is r cos theta, which is 2 times the cosine of minus pi by 3, which is equal to 2 times, now we want the cos of minus pi by 3. And the cosine of minus pi by 3 is 1/2. And so that gives us 1. Y is equal to r sine theta, which is 2 times the sine of minus pi by 3, which is 2 times, now we want the sine of minus pi by 3, and that is minus root 3 over 2. And the 2's cancel to give us minus root 3. And so again, notice we know that we've got it in the right quadrant, because when we drew the diagram, we have positive x and negative y, and that's how we've ended up here. What do we do about going back the other way? Well, let's have a look at some examples that will do that for us. What I'm going to look at are these points which are Cartesians. The point 2, 2, the point minus 3, 4, the point minus 2, root 3, and the point 1, minus 1. Now these are all points in Cartesians. So let's begin with this one. Show where it is. To begin with, on the Cartesian axes, so it's at 2 for x and 2 for y, so it's there. So again, we'll associate the origin in Cartesians with the pole in polars and the x-axis with the initial line. And what we want to calculate is what's that angle there and what's that radius there. Well, r squared is equal to x squared plus y squared. So that's 2 squared plus 2 squared gives us 8. And so r is equal to 2 root 2 when we take the square root of 8. What about theta? Well, tan theta is equal to y over x. And in this case, it's 2 over 2, which is 1. And so theta is pi by 4. And so therefore, the polar coordinates of this point are 2 root 2 pi over 4. Let's have a look at this one now. Minus 3, 4. Let's begin by establishing whereabouts it is on our Cartesian axes. -3 means it's back here somewhere, so there's -3, and the 4 on the y, it's up there. So our point is there. Let's join it up to the origin. There's our point P, and we are after now the polar coordinates for this point. So again, we associate the pole with the origin and the initial line with the x-axis. And so there's the value of theta that we're after, and this OP is the length r that we're after. So r squared is equal to x squared plus y squared, which in this case is -3 squared plus 4 squared. That's 9 plus 16 gives us 25. And so r is the square root of 25, which is just 5. What about finding theta now? Well, tan theta is y over x, which gives us 4 over -3. Now, when you put that into your calculator, you will get a slightly odd answer, because it will actually give you a negative answer. That might be difficult for you to interpret, because it's actually telling you this angle out here, and we want to be all the way around there. Now, the way that I think these are best done is actually to look at a right-angled triangle like this and call that angle alpha. Now let's have a look at what tan alpha is. Tan alpha is 4 over 3, and when you put that into your calculator, it will tell you that alpha is 0.93 radians. Remember, theta has to be in radians. And that therefore theta here is equal to pi minus alpha, and so that's pi minus 0.93, which gives us 2.21 radians. And that's theta. So you can see that the calculation of r is always going to be relatively straightforward. But the calculation of this angle theta is going to be quite tricky, and that's one of the reasons why it's best to plot these points before you try and work out what theta is. Now, our next example was the point -2 root 3. So again, let's have a look where it is in the Cartesian plane. These are its Cartesian coordinates. So we've -2 for x, so we're somewhere back here, and -2 root 3 for y, so we're somewhere down here. So our point is here. Let's join it up to our origin and mark in our point P. Again, we'll take the origin to be the pole and the x-axis to be the initial line. And we can see that the theta we're looking for is around there. That's our theta, and here's r. So again, let's calculate r squared. That's x squared plus y squared is equal to, well, in this case we've got -2 all squared plus -2 root 3 all squared, which gives us 4 plus 12, 16, and so r is equal to the square root of 16, which is just 4. Now, what about this? We can see that theta should be negative. So let's just calculate this angle as an angle in a right-angled triangle. So tan alpha equals, well, it's going to be the opposite, which is this side here, 2 root 3 in length, over the adjacent, which is just 2, which gives us root 3. So alpha, just calculated as an angle, is pi by 3. So if that's pi by 3, this angle in size is 2 pi by 3. But of course we must measure theta negatively when we come clockwise from the initial line. And so theta is minus 2 pi by 3. The 2 pi by 3 giving us the size, the minus sign giving us the direction. So we can see that the point we've got described as minus 2 root 3 in Cartesians is the point 4 minus 2 pi over 3, or minus 2/3 of pi in polars. Now we've taken a point in this quadrant, a point in this quadrant, a point in this quadrant. Let's have a look at a point in the fourth quadrant just to finish off this set of examples. And the point we chose was 1 minus 1. So again, let's have a look at where it is in our Cartesian system. So we've a value of 1 for x and a value of minus 1 for y. So there's our point P. We join it to the origin, and again we'll associate the origin in the Cartesians with the pole of the polar coordinates, and the initial line will be the x-axis. So we're looking for this angle theta and this length of OP. So r squared is equal to x squared plus y squared. So that's 1 squared plus minus 1 squared, and that's 1 plus 1 is 2. So r is equal to root 2. Let's not worry about the direction here. Let's just calculate the magnitude of theta. Well, the magnitude of theta, in fact, to do that, I'd rather actually call it alpha. I just want to calculate the magnitude. So tan alpha is opposite, which is 1, over the adjacent, which is 1, which is just 1. And so alpha is, in fact, pi by 4. That means that my angle theta for the coordinate coming around this way is minus pi by 4. And so my polar coordinates for this point are root 2 and minus pi by 4. So we've seen here why it's so important to plot your points before you do any calculation. Having looked at what happens with points, let's see if we can now have a look at what happens to a collection of points. In other words, a curve. Let's take a very simple curve in Cartesians. X squared plus y squared equals a squared. Now, this is a circle centered on the origin of radius a. So if we think about that, a circle centered on the origin of radius a. So it will go through these points on the axis. Like so. Now, if we think about what that tells us, it tells us that no matter what the angle is for any one of our points, if we were thinking in polars, the radius is always a constant. So if we were to guess at the polar equation, it would be r equals a, and it wouldn't involve theta at all. Well, let's just check that. We know that x is equal to r cos theta, and we know that y is equal to r sine theta. So we can substitute these in. R squared cos squared theta plus R squared sine squared theta is equal to A squared. We can take out the R squared and that leaves us with this factor of cos squared plus sine squared. Now, cos squared plus sine squared is a well-known identity. Cos squared plus sine squared of the same angle is always 1. So this just reduces to r squared equals a squared, or r equals a. R is a constant, which is what we predicted through looking at the situation there. Now, another very straightforward curve is the straight line, y equals mx. Let's just have a look at that. Y equals mx is a straight line that goes through the origin. The thing about it is it has a constant gradient. And of course, m, the gradient, is defined to be the tangent of the angle that the line makes with the positive direction of the x-axis. So if the gradient is a constant, the tangent of the angle is a constant, and so this angle theta is a constant. So let's just have a look at that. Y is, we know, r sine theta equals m times by r cos theta. The r's cancel out, and so I have sine theta over cos theta equals m, and so I have tan theta equals m, and so theta does equal a constant. But, and here there is a big but, for y equals mx, that's the picture that we get if we're working in Cartesians. But if we're working in polars, there's our pole, there's our initial line. Theta equals a constant. There is the angle theta. And remember, we do not have negative values of r. And so we get a half line. In other words, we only get this bit of the line, the half line there. That simple example should warn us that whenever we're moving between one sort of curve in Cartesians into its equivalent in polars, we need to be very careful about the results that we get. So let's just have a look at a couple more examples. Let's take x squared plus y squared is equal to 9. We know that x is r cos theta and that y is r sine theta. We can plug those in. R squared cos squared theta plus r squared sine squared theta equals 9. R squared is a common factor, so we can take it out, and we've got cos squared theta plus sine squared theta is equal to 9. Cos squared plus sine squared is an identity. Cos squared plus sine squared of the same angle is always 1, and so r squared equals 9, or r is equal to 3, i.e. a circle of radius 3. Let's take the rectangular hyperbola. xy is equal to 4. And again, we're going to use x equals r cos theta and y equals r sine theta. So we're multiplying x and y together, so when we do that we're going to have r squared sine theta cos theta equals 4. Now, sine theta cos theta, well, twice sine theta cos theta would be sine 2 theta. But I've taken 2 lots there, so if I've taken 2 lots there, it's the equivalent of multiplying that side by 2, so I've got to multiply that side by 2. So I end up with that for my equation. Let's do some the other way round now. But one point to notice before we do. Knowledge of trig identities is very important. We've used cos squared plus sine squared is 1, and we've now used sine 2 theta is equal to 2 sine theta cos theta. So knowledge of those is very important. So, as I said, let's see if we can turn this around now and have a look at some examples going the other way. First one we'll take is 2 over r is equal to 1 plus cos theta. I don't like really the way it's written, so let's multiply up by r. So I get r plus r cos theta. Now because I've done that, let's just remember that r squared is equal to x squared plus y squared. So that means I can replace this r here by the square root of x squared plus y squared. R cos theta, well, r cos theta is equal to x. So I can replace this bit by x. Now, it looks untidy. It's got a square root in it. So naturally, we would want to get rid of that square root. So let's take x away from each side. And then let's square both sides. So that gives us x squared plus y squared there. And on this side, it's 2 minus x all squared, which will give us 4 minus 4x plus x squared. So I've got an x squared on each side. That will go out. And so I'm left with y squared is equal to 4 minus 4x. And what you should notice there is that's actually a parabola. So this would seem to be the way in which we define a parabola in polar coordinates.